Science Matters. Hi, I'm Lawrence Krauss, and I'm incredibly excited by this episode because I'm going to take you from the origins of life to the outer limits of the universe and back to the fundamental structure of matter and the weird and wonderful world of quantum mechanics and how it's affecting technology today. Hang on to your hats because each of the three things I'm going to talk about is progressively a little bit more complicated. So by the end, your head may be spinning, but I want to try and talk about things I've never actually talked about on television, and I hope you can stay with me because they're incredibly exciting. Now, the first thing I want to talk about is the origin of life. A subject of great interest in current science because we really don't know how life originated, but we're getting closer and closer. If you can look at the first image here, what you see is an artist's rendering of what Freeman Dyson once called a bag of garbage. Because that's what Freeman said life originally was. You see, there's lots of debates as we try and understand exactly the earliest moments where chemistry turned into biology. We know that life is based on proteins and RNA and DNA, and for a long time there was a debate about which formed first, and most, I think, scientists now think an RNA world occurred before a DNA world. But even RNA is an incredibly complicated molecule. How do you get from just a world of organic materials naturally occurring to RNA? Well, one of the first steps is to separate out the organic materials from the surrounding worlds with what's called a protocell. And Dyson labeled that protocell just a bag with a bunch of garbage in it. Because really he was saying that what you needed is that first separation, that first membrane. Now, for a long time, scientists realized you could form natural membranes that would separate the world where the chemistry of life might be occurring from the outer world of water or air or whatever else, because materials called fatty acids naturally form spherical membranes. There's a reason for this. Fatty acids are basically made of materials that look a little bit like a tadpole. At one end is the large end, which is sort of has an affinity towards water, and the little line like the tail of the tadpole doesn't like water. And if you have some water and you have a few of them together, what will happen is, of course, is that the head end of the tadpole will be attracted to the water. The tail end will move away from it. Now, if you put a bunch of these things together, what naturally will happen then is that you'll end up forming a spherical membrane where the outer part of the membrane is just the heads of the tadpoles, and the inner part, largely hollow, just has these little tails, and these naturally form in water. So people thought, okay, well, fatty acids can be the membranes which create the protocells from which the chemistry of life eventually evolved. But there's a problem. In water, you're fine. But if you have salt water or water with magnesium or iron or any of these things, it turns out it's been observed that fatty acid membranes just collapse. They're not stable. And of course, in the early oceans, salt water was there, and these fatty acid membranes would fall apart. And this was a huge concern, and people really didn't know how to get around it. By accident, one day, Caitlin Connor, a student working for Sarah Keller at the University of Washington, observed actually, as she was largely by accident looking at fatty acids in configurations of salt and magnesium and things like that, but also in configurations where there are other things like amino acids, discovered something amazing, magical, as they called it, and it is magical. If you have amino acids, which are the basis of proteins, which basically are the workhorses of modern biology, essential for life, when you put amino acids and fatty acids together, these fatty acid membranes become stable in salt water and magnesium. So what would otherwise be unstable suddenly becomes stable when you put together the two major components of life, amino acids and fatty acid membranes. These things only are stable if you have exactly what's needed to eventually produce the machinery of life. And in these membranes, it's a long way from a membrane with amino acids to membranes that have RNA and DNA. That's a long way, and we don't necessarily know how to get there. But the first stage basically says, if you have configurations which have the components necessary for life, then it's stable. It's magical that the two things that are required only work when they're together. They found it magical. I find it magical. And I hope you find it magical, because it's a big step in understanding potentially how life arose and how you went from chemistry to eventually the miraculous biochemical machines that we are. One small step for two scientists at the University of Washington, but perhaps a giant leap for mankind. Now, the next thing I want to talk about has actually been in the news a lot, and I want to describe it. If you may have read a lot of articles that saying the Big Bang is in trouble. There's something really problematic. And I want to present to you the problem, and we can see together whether we think it's a real problem. It has to do with the fact that different ways of measuring fundamental quantities in our universe, in particular one fundamental quantity, the expansion rate of our universe, appear to give somewhat different answers, and that's impossible unless something very strange is happening with the universe, or unless one of the experiments is wrong a little bit. So I want to show you the problem. This is a picture I've often shown. It's an image of the cosmic microwave background. It's projected on a plane. It's the microwave background coming at us from all directions, spherically coming at us from the Big Bang in all directions, and that sphere is projected on a plane just like a globe of the Earth is projected on a plane when you look at maps of the Earth. And the center of it, a horizontal line on the center, would be where our galaxy is. And the top of the image would be looking up, and the bottom of the image would be looking down. Now, when you look at this comes from the Planck satellite, which is the highest resolution satellite that's looked at the cosmic microwave background. And you see lots of red and blue, very small splotches. These are primordial fluctuations in the cosmic microwave background that come from the beginning of time. It's incredibly exciting, and this has changed cosmology because these can be measured with such high resolution now, parts in 10,000 or 100,000, that has allowed us to measure the parameters of cosmology in a way we wouldn't thought was possible before. The blue and the red are slightly different temperatures. This average background is 3 degrees above absolute zero, approximately 2.73 degrees above absolute zero. The differences between the red and the blue are more like 1 part in 100,000 of a degree. So they're very, very small fluctuations, but they would later collapse to form all the galaxies, clusters of galaxies, stars, and eventually us. So this is an amazing image of the cosmic microwave background, and because it has such high resolution, astronomers have been able to measure the parameters of cosmology, as I say, in a way that I would never have thought it would be possible when I was a graduate student. Now, I don't expect you to understand this picture, but what this image shows is basically the size of the lumps on the sky, how many of them there are on different sizes, different angular scales. So the number here at the bottom is L, but L of 100 is about 2 degrees, and as L gets bigger, the angular scale gets smaller, and as L gets smaller, the angular scale gets bigger. So it's really counting lumps, and you can see most of the lumps have an angular scale about 1 or 2 degrees, and that comes from physics. It turns out the primordial physics of what was happening when that cosmic microwave background was formed will pick out a scale of about that size. I'm not going to go into the details here because they're not that important, and I've discussed them in my books and in other places. But what you can see is how the data is incredibly precise. And not only and you can see that there are these little waves. They're called acoustic oscillations as matter began to collapse and expand and collapse and expand in the early universe. And you can see not just the first peak, but the second, the third, the fourth, the fifth, and the sixth. And by using this, astronomers have been able to fit to cosmological models to try and determine not just the age of the universe, but the expansion rate of the universe, the amount of normal matter in the universe, the amount of dark matter in the universe, and even the amount of dark energy in the universe. Fitting it all together, you can try and measure parameters and relatively precisely. And one key parameter that comes out of this, given that the universe has expanded from the time the cosmic microwave background was created to today, is the expansion rate of the universe today. And this allowed us to measure for the first time the expansion of the universe today to high precision. But there's a problem. This is an indirect measurement of the expansion rate of the universe by observing the universe on all scales and plugging in cosmological models and deducing the expansion rate of the universe by measuring over the entire universe. There's another way, of course, to measure the expansion rate of the universe. It was the first way that was done by Hubble and has been repeated since then, and that is to look at nearby objects and see how fast they're moving away from us as a function of their distance from us. It's the discovery Hubble made in 1929, and it's been refined ever since by trying to use objects whose intrinsic brightness we know. Because if we're going to see how fast objects are as a function of how far away they are away from us, we have to know how far away they are from us. but how can you tell how far away they are from us? The way it's done is by something called a standard candle, something whose intrinsic brightness we understand, and then you look at it through a telescope and you see how bright it looks through a telescope, and from that you can deduce how far away it is. And so we can measure the expansion rate of the universe as a function of distance. That's the way it's always been done. And it's been refined and refined. The first objects that were used were these objects called Cepheid variable stars that vary in brightness as a function of their period. And by the period of their variation, you know how bright they are. And Hubble looked at them in nearby galaxies, and ever since then, astronomers have used better and better techniques to look at those objects to try and measure the expansion rate of the universe. Then another standard candle came along, exploding stars, supernovae. It turns out supernovae of a certain type we believe have a known luminosity, and we can see them across the universe, so you can try and measure the Hubble constant to far distances. And a new technique has just come along. This is how astronomers do it. These are 3 different galaxies, and astronomers can try and measure stars in the outskirts of those galaxies and look at specific stars they believe they know the brightness of. These are not Cepheid variable stars. It turns out stars, as they age, eventually certain stars go along what's called a main sequence branch, and then they become red giants. And at the moment that a star becomes a red giant, which is when it essentially stops burning hydrogen and begins to burn helium, these stars are believed to have a known luminosity. And most recently, there was a new set of studies of very carefully of what's called the turnoff of red giants. These are all red giant stars, looking at their brightness, how bright they appear to be in the telescopes. And you can then tell how far away these galaxies are, and gave a new measurement of the Hubble constant. Well, what's all this give? This is the problem. This is the problem that's been written about in newspapers. And some people suggest there's something dramatically wrong with cosmology. If you look up at the upper left-hand side, you will see the measurement of the Hubble constant, the expansion rate of the universe, in this series of units called kilometers per second per megaparsec that don't matter for our purposes. When I was a student, this number was known to within a factor of 2. Some experimenters found it to be 50, some found it to be 100, and it was known to within a factor of 2 uncertainty. Now it's measured to be 67.4 plus or minus 0.5, at least according to the Planck satellite, and another satellite doing very similar things, using different techniques looking over the large scale of the universe, not just the Planck satellite, but using other techniques to measure large scale structure, finds a similar number. So by measuring over the whole universe, you get a number that's 67 plus or minus about 1. The problem is when you use these other techniques of measuring Cepheid variables to measure the local expansion rate of the universe, you come up with a number that's closer to 72 or 73. Now, the question is that a problem? If you're as old as me, the natural tendency is to say it's not a problem. Because as I say, when I was growing up, a certain set of astronomers measured the number to be 50 plus or minus 5. Another set of astronomers measured the number to be 100 plus or minus 5. And clearly, they couldn't both be right. In fact, many of us said, well, the real answer is going to be about 75 because it's halfway in between. And that turned out to be about right. It's very hard to measure this. And in astronomy, there are not just statistical errors, there's something called systematic uncertainties, because you can't fiddle all the knobs when you come to stars. Maybe there's dust that you can't see. Maybe a certain type of star out there is not the same as a star nearby. So there are all sorts of systematic uncertainties. But the astronomers who've measured with Cepheids have claimed that they've reduced the systematic uncertainties, so their best number is around 73 plus or minus 1. When you look at those two numbers and try and compare 67 to 73, they vary by what's called between 5 and 6 sigma, which means that the likelihood that both of them, that they could both be measuring the same number, is less than 1 part in a million. And that means that if this is right, the number that's extracted from the early universe is vastly different than the number that's extracted from local observations, and there's no sensible way we know of to explain that. The universe would have to be doing something very strange in its expansion in a way that no theory predicts. I mean, of course, theorists have come up with ideas, but they're all pretty crazy. So this was a situation as of about 2 weeks ago when there was a big meeting where both sets of astronomers were there to try and argue with each other. But what happened? If you look right up there at this red measurement, CCHP, it was a new measurement that has to do with the measurement of this red giant turnoff branch, done by Wendy Friedman, who's been measuring the Hubble constant. She was in charge of the Hubble Key Project survey, which used the Hubble Space Telescope to measure the Hubble constant. Her number falls halfway in between. If you look at this, you can see how the data has gotten better over the years with the error bars. In 2000, the error bars were so great that the difference between the measurements with the cosmic microwave background and Cepheid variables were indistinguishable. But over time, astronomers have been measuring things very much more carefully, and you can see that the Cepheid number, the uncertainties got much smaller, and as did the uncertainties in the CMB once we got satellites like Planck, and the two are very different. And that difference has been claimed by certain astronomers to mean there's something fundamentally wrong with cosmology. What's just happened to muddy the waters, or maybe clarify the waters, is this new measurement of the local expansion rate using red giant turnoffs has come right in the middle. And maybe that means that there is some systematic uncertainty that one or the other of those two techniques is wrong. Now, to get a real sense of that perspective, I want to show you an image that just tells you how precisely this has to be measured in order to tell the difference between those two different values of the Hubble constant. This is an image like you saw before from the cosmic microwave background. It comes from two different satellites, one the Planck satellite and another satellite before it called the WMAP satellite. And those two gave slightly different numbers for the Hubble constant by measuring the cosmic microwave background. One was 67, one's about 70 or 71. But I want to show you where the difference comes from. One of them is a dash curve and one of them is a solid curve. And it's that difference between those two in the fourth and fifth and higher bumps where that almost imperceptibly small difference can give the difference between 67 and 70. So that tells you how carefully you have to measure not just the cosmic microwave background, but other things to tell the difference between 67 and 73. So the key question is this difference forcing us to say that cosmology as we know it is wrong and there's something new beyond dark energy that has to change our picture of the expansion of the universe? Or could it be some systematic effect that the observers haven't yet taken into account? I have to say that, like most things, I'm agnostic in this area. I tend, however, given my age, to fall in the camp of thinking it's probably systematics. After all, I came from a time when we used to know the Hubble constant was either 50 or 100 and to claimed high accuracy, and it wasn't anywhere near the two. But this is the accuracy you have to measure, and the astronomers claim now that they can measure that level of accuracy. So we don't know where the problem lies. But I wanted to show this to you because you'll hear a lot in the literature and if you read and hear the news that there's some fundamental problem in cosmology, that things don't work. Well, the observations are inconsistent, but you have to decide for yourself if we should yet throw out the standard model of cosmology because of that inconsistency, or, as hinted by the new observation of red giant turnoffs, maybe it's the observations themselves that have some problems. We'll see. Stay tuned. Okay, the last topic takes me to quantum mechanics. And if your head wasn't spinning before, it'll spin now. Quantum mechanics is crazy. It'll always be crazy, and that's just the way the world works. What I want to talk about is a topic you may have heard about called quantum teleportation. I remember I got a call about this after I wrote a book on the physics of Star Trek. 10 years later, a newspaper said, physicists have just teleported the state of one atom or one electron or one photon from one place to another. Doesn't that violate everything you wrote about in the physics of Star Trek? Well, of course it didn't, but it opened up an incredibly new and exciting possibility based on a really weird aspect of quantum mechanics. And what this photograph is schematically showing is potentially, can you teleport the state of a bit of light from one place to another? Not just two jars in the same room, maybe, but from here to a satellite or maybe Alpha Centauri. Quantum mechanics, in principle, allows you to teleport instantaneously two photons and make sure that the quantum state of one is reproduced exactly in the other photon instantaneously, not at the speed of light, but instantaneously. It sounds like it violates all common sense, logic, and physics, but it doesn't. And I want to talk about that because there's been a new development in quantum teleportation, and this could be important for, among other things, your bank accounts and other things into the future. But it's going to require me to talk a little bit about quantum mechanics. So, the teleportation relies on something called entanglement. And it's something that Einstein hated so much he called it spooky action at a distance. And it is the following. If I create a quantum mechanical state, say 2 electrons in some initial state where, say, their spins are aligned or anti-aligned, and I carefully prepare them, well, it turns out, let's say they're anti-aligned like this. Well, it turns out that they can be anti-aligned, but of course they can be pointing in any direction as long as they're anti-aligned. And classically, of course, they exist in one such state. And if I measure them, I'll find out that one is pointing in that direction and one is pointing in that direction. But it turns out quantum mechanics tells us before we make the measurement, they've actually been pointing in all directions at the same time. And it wasn't until I make the measurement that I actually force them to be in one specific configuration. Before that, they're in all directions at the same time. It's crazy, but true. Now, here's where the weird spooky action at a distance comes in. Let's say I separate those, say, electrons, if that's the particle in question, from here to Alpha Centauri, and of course they're still entangled, so they're still pointing in opposite directions, and they're pointing in all directions at once. But now let's say I measure this one and find out it's pointing in that direction. That means instantaneously this one has to be pointing in that direction, because they point in opposite directions. Before, they were in all directions at once. Afterwards, boom, I measure this. I instantaneously force this to be pointing in this direction. Okay, this is a spooky action at a distance. Now, this may sound like you can transfer information instantaneously at the speed of light. Turns out you can't. I'm going to try and explain it here. Hopefully, I can. The point is that if I have an experimenter over here, and they're measuring the spin of this particle sort of 50% of the time when they measure, it'll be pointing up. 50% of the time, it'll be pointing down in the lower hemisphere because it's pointing in all directions. So if this person measures this particle, 50% of the time, they'll find it spinning in the upper hemisphere, 50% of the time in the lower hemisphere. Well, what will this experimenter find? 50% of the time, when they measure the spin of this particle, it'll be pointing in the upper hemisphere. 50% of the time, it'll be pointing in the lower hemisphere. So this person makes a measurement, boom, and then this one makes a measurement and finds it's pointing in the lower hemisphere. But there's nothing that tells him that there's anything different about it, because the next one may be measured to point in that direction, and this one will be pointing up. The only way that this person can know anything strange has happened is if the first experimenter picks up the phone, calls the second experimenter, and says, when you measure this particle, you will find it pointing in that direction. And of course, they measure it and find indeed its spin pointing in that direction. So the only way that this experimenter can know anything crazy is happening is if the first experimenter makes a telephone call or something like it. That happens at the speed of light. So no information can travel faster than the speed of light. You're not violating relativity or anything. The spooky action at distance can occur instantaneously, but not be observable without communicating causally between those two observers. Now, this effect, this entanglement effect, has now been used for what's called quantum teleportation. Because if I have these two particles that are entangled, let's say 2 bits of light that I initially created with a mirror, one going off in one direction, one going off in another direction, with specific properties, if they're now far apart, and now I let this first photon, this first particle light, interact with another photon whose state I fixed, it's now interacted with it, and say it's now forced to be in the same state as this photon, this will suddenly be forced to be in the same state as that photon. So what I will do is recreate the quantum state of my first particle by using the entanglement of the other two particles. That's quantum teleportation, and it's been observed and measured. And in fact, experimenters have been able to recreate quantum states of particles like electrons or ions or photons, very carefully prepared quantum mechanical configurations, not just here, but actually teleport that information, if you want to call it, the quantum state of the initial particle, up to a satellite and back. Now, why is that important? Because if you can do that, you can basically transport quantum information from one place to another. And if you do anything in the middle, if you try and eavesdrop, if anyone tries to figure what's happening, you'll destroy that quantum coherence in a way that the observer here will know something has happened. So it allows you to send messages that are very secure. And of course, when we're transporting information like banking information or other things, we want to know if someone is intercepting it in the middle. And if we could use this quantum property to transport the information, that would be very important. I happen to think quantum teleportation is going to be much more practical in the coming years than quantum computers, which you hear about a lot more. That technique, I think, will be manageable and useful, and will actually be employed by physicists and engineers to help us in the relatively near future. By the way, the key aspect of quantum teleportation is the word quantum. You have to have a very specially prepared quantum mechanical state. And so when we talk about teleporting humans, it ain't going to happen because we're not very specially prepared quantum mechanical states. We're quite classical objects. If you take an electron in a very special state, it can go to a wall, and every now and then it'll tunnel through the wall. I guarantee you that you can run towards a wall from here to the end of time, and you'll never find yourself tunneling through it. You'll bounce off it. So quantum teleportation is great for very specially prepared quantum mechanical states, but it's not going to allow Spock or Kirk to go from the Starship Enterprise to a planet. Now, I wanted to talk about this in general, but I wanted to tell you that if that wasn't complicated enough, what experimentalists have just achieved is something that may make this even more important for information transfer. A photon has a spin in one direction or another, an electron has a spin in one direction or another, and that's quantum information in the sense that it's a 1 or a 0. It's a quantum bit of information, so we call it a qubit, not a bit. A regular bit, 1 or 0, we call a bit. But a quantum mechanical bit, we call it a qubit because it contains more information because it can be in many states at the same time, but it's still either up or down eventually when you measure it. What physicists have been wondering is, can you take quantum mechanical systems that have more than just an up and a down? And what was just done was to teleport a system that had 3 degrees of freedom. And those 3 degrees of freedom depend on another property of quantum mechanics that I'm going to tell you about right now, which is really at the basis of quantum mechanics. And then we're almost done. So let's look at the next slide. The thing that makes quantum mechanics so strange is the following. If I take bullets and shoot them at a screen with 2 holes in it and have a wall on the other side, of course, what you'll expect to see is the bullets that go through the one hole will cause a dent in the wall on one side, and the bullets that go through the other hole will form a dent on the other side. If you send waves through, like light, it's been shown, of course, and this is high school physics, when you go through 2 narrow slits and you send light rays, the waves form and the waves will interfere, and what you'll see is not one bright spot behind one slit and a bright spot behind the other slit, but rather a series of lines, what's called an interference pattern. What's remarkable is if I take electrons and do it, you'd think electrons are particles. If I sent them through, I'd see just one spot on one side. If I had a TV screen which lit up when electrons hit it, you'd see a bright spot behind it and a bright spot behind that. But what, of course, the property of quantum mechanics tells us that matter behaves like waves, and in fact what you see is not 2 bright spots, but an interference pattern, telling us the electrons are acting like waves. And what's really weird, you say, but hold on, electrons are particles. They have to go through one slit or another. And I can tell if they go through one slit or another. I can put an electron detector at both slits. I can send electrons through, and boom, it'll click when an electron goes through one slit or another. And you'll say, see, the electrons didn't interfere with each other because they went through one slit or another. A single electron going through can't have gone through both slits at the same time. It went through one slit or another. And when you do that, though, when you put the counting mechanism in, you then look at the screen and the pattern has changed. It's got 2 bright spots. So it tells you, just like the particles spinning in all directions at the same time, when you don't measure the electrons going through, each individual electron is going through both slits at the same time. And if you measure it, of course, you'll find it having gone, if you measure it in the middle, you'll find it going through one slit or another. But if you don't measure it, it's in what's called a superposition state where it's going through both slits. Well, what you might imagine is the experimentalist, this is a complicated graph, and I don't expect you to understand the details, but what experimentalists have just done is not take electrons, but light, sent light rays through a system with 3 slits. Now, the light rays, being quantum mechanical particles, the individual photons, go through all slits at the same time, and the quantum mechanical state is a superposition of those. Okay? But once again, you can measure the light ray in the middle and find out which slit it went through. So what you've created is basically a light ray that has 3 different degrees of freedom. One's either whether it went through one slit, the other slit, or the third slit. So you either have not 0 or 1, but 0, 1, or 2. And what experimentalists have done is basically entangle 2 light rays, creating 2 light rays that are entangled, moving them apart, and allowing them to go through this system with 3 slits. And then by interacting with another particle, the so-called reference particle, and in this case it's 2 particles because of the complications of quantum mechanics, you basically force one of those teleported particles to be in a specific state, and it forces the other particle, the other particle of light, the other photon, if you wish, to have exactly the same state as the first pair. And that means they've teleported information, quantum information that has 3 degrees of freedom. If you increase from 2 to 3 degrees of freedom, you can contain a lot more information, and this is maybe the first step on allowing us to use quantum mechanics to realistically transfer information that may be useful for not just banking systems, but for any other individual or organization or country that wants to transfer information in secret, coded in a way that can't be intercepted by others. And what I wanted to, so this was just came out. It's complicated, but what I wanted to point out is by exploiting the weird and wonderful properties of quantum mechanics, we're now able to do quantum teleportation for systems that are more complex. Not complex enough to be a human being, but complex enough to change the dynamics. And in the process, I tried to explain to you some of the weirdness of quantum mechanics and the weirdness and the strangeness of the universe, as weird as it may be, is being exploited by us today. We're using the remarkable features of the universe to create technologies of the future and to learn about not just how life began, but how the universe began, and ultimately to affect the future of mankind. Science matters. Thanks a lot.
The Origins podcast is produced by Lawrence Krauss, Nancy Dahl, Amelia Huggins, John and Don Edwards, and Rob Zepps. Directed and edited by Gus and Luke Holwerda. Audio by Thomas Amison. Web design by Redmond Media Lab. Animation by Tomahawk Visual Effects. And music by Rickolas. To see the full video of this podcast, as well as other bonus content, visit us at patreon.com/originspodcast.